Yeah, or you can call me Shri. Yeah, yeah. All right. So we're gonna be going over chapter 5, symmetries. I guess we just jump into it. Um, this is my first time actually just giving any sort of, I guess, lecture. I've done reading groups in the past, but it'll be interesting to see how this goes. Sort of like a practice run for the future ones. But if it hasn't been obvious the way that we've just been studying in algebra, I guess coming from like a geometrist side or geometrist perspective, I like to see this as like kind of like a written geometries, which is literally what the quote says, which is why I found it so fascinating. I don't know if you saw the quote at the beginning of this chapter, but of such, we have these like concepts called like symmetries, which are kind of like triangles, squares, like kind of pen and compass transcriptions. And we also have these like three different types of symmetries that we're specifically, or I think four types of symmetries that we're going to be looking at, which is bilateral, um, translational, glide, and rotational. So these four different types of symmetries is where you could have something bilateral is when you split it down the middle, so like a heart. Translational is when you just take a like a some sort of figure and move it to a different location. Glide, the textbook kind of just shows it as being able to have a symmetry across both rotational as well as translational, kind of like an in between or like a reflection moved forward. And then last but not least, rotational is literally just if we take any sort of figure, how can we rotate it such that it would always look the same? And it usually will look the same every single rotation or every single discrete rotation, which we'll talk about later on. Um, but outside of that, we have these concepts called isometries. So I don't know if anyone's done this in the past, but does anyone want to answer what an isometry is from the text? No? Okay. Okay. All right. Well, I guess that won't work. But an isometry is just I guess like an informal definition. We could just say it's like a rigid motion of the plane. And what we mean by like a rigid motion is that if we take like say a pack of gum, we could rotate this in any sort of format such that if we were to plop it straight down, it's going to look one way. We could rotate it and also plop that straight down and it'll look another way. It's literally just a taking and figure an object of any sort of shape or form, and you are just kind of mixing with it, but nothing that actually changes the figure itself, like alters it in any sort of like way, that makes it look different in any sort of way, other than just the fact that we're doing rotations, reflections, and translations most of the time, at least. Um, and with these isometries, we have these concepts called symmetries, as we mentioned before. So a symmetry is if we take these isometries, so if we take these isometries and this isometry has the figure itself as the subset of this plane to itself. So we're basically just taking, like, for example, let me write this down officially. The tree has the figure, or instead of saying a figure, we should probably say a subset of the figure of the figure to itself, then then this is a symmetry. Okay. So what do we mean by taking like a subset of the figure itself to the plane itself? Um, subset of the figure of the plane to itself. So if we were to take, for example, let's take that same exact hexagon that we had before. And we have an isometry would just be a rigid motion of a plane. So we have a set of isometries. So these isometries can be elements that look like, for example, or I should probably take a different shape that doesn't actually have rotational symmetry. Let's take this like little L block. We could rotate this L block in any sort of way, and it's gonna have a sort of symmetry. It's gonna have some sort of like symmetry that's gonna be in the set of isometries. This is literally just a rigid motion. So I'm gonna take this subset. We could also always have more subsets in the plane. So we could have this be translational, which means we're just moving it across the plane, or we could also have reflection isometries, but we're just taking a subset of this figure or this isometry, and we take this subset and we map it to some sort of place on the plane itself. And this itself would be a symmetry. So all of these are symmetric in the regards that, oh, this isometry is just literally taking, or with the subset of the isometry is literally just having some sort of rotational basis, but these are all the same figures. These are all the same. This all has the same properties. This doesn't look anywhere jarring. Um, and in fact, the set of isometries or the set of symmetries, um, symmetries is literally equivalent to all the different subsets of the isometries themselves. Isometry 1 or and then isometry 2. Um, yeah, and we're literally grouping these isometries by what sort of basis we're doing these rigid motions on. This could be both. This could be, as we said before, but it could also be the combination of these, like a translation and a reflection, or a rotation and a reflection, and just so forth. It's just each of these isometry, I guess, groups themselves, we're actually classifying these as groups, are in fact just having, I guess, sort of a, I guess, as a group is defined, we have a complete bundle of these, of these, like, I guess, is there a word for this? I guess these rigid motions themselves. I think that's the only word that we actually are dealing with. All right. So, um, So we're saying that specifically both the symmetries and the isometries themselves are groups. So the reason why we're saying such is that, for example, later on with this topic, we'll go ahead and explain why it's a group itself. But we have, like, for example, say, let's just say like a reflection is noted as R for reflection. We have a rotation noted as rho of theta. There's these properties that comes with groups, and we're going to have like these sort of actions or these group operators that allows us to combine these reflections and rotations. So we're specifically calling these both as groups, or these isometries as subgroups of symmetries, because of the fact that they're complete sets of just having one operation that is both operationally closed, both it has an identity mapping, and as well as just has a, yes, I believe it has to have an inverse, yeah. So yes, it does have an inverse, yeah. So if it hasn't been something that hasn't been like established already or hasn't been clear, I'm saying specifically that we have group operationally closed, because we probably dealt with groups such as having like addition and multiplication closed. And this just means that if you add two things, that it's also going to be in the set itself. If you multiply two things, it's going to be in the set itself. We have those groups that still exist, but then when we get into these things with symmetries and like rigid motions of the plane, um, we're dealing with sets that specifically just are combining different rigid motions, which we can look at it as multiplication, which will denote it as multiplication later on, but it's not entirely just saying, oh, we're multiplying a translation of the figure to the rotation of another figure and making that within the set itself. So I like to just generalize it to say it's group operations. And I'm not too sure if this was, I guess, talked about in the course so far, other than just like saying like, oh, we're dealing with group operations that are multiplication and addition. We're now dealing with group operations that are specifically just, I guess, taking these rigid motions and compiling them together in the form of like composition. So um, I haven't watched too. I kind of skimmed through the previous videos. I don't think I've seen anyone talk about like group operations of like say compositions or exponentiations, but that's something that's definitely going to be going on in the course later on. I think this is more so just like a sort of rough idea in order to start introducing that topic, but not super advanced early on. But I guess getting back on topic, I hope that answers your question. Okay, cool, cool. Does the term rigid motions exclude the reflections? No, no, that's actually a great question. So I'm specifically focusing on like translations and rotations, but it doesn't mean that it's not reflections themselves. So we could have, for example, let's just say this is the isometry of rotations. So let's just say this is that. We could also have a isometry of reflections. So if we had the same exact L block, we also have its reflection. And similarly, we're going to only have two elements in this reflection subgroup, but it also helps that, oh, even though it's two elements, it has its identity, which is E here, and its second element, wherever we're going to note it as, um, the reflections are always, or are still going to be included in this group of rigid motions. Fun fact, when you go into a higher dimensional rigid motions, you can have other types of rigid motions too, which is kind of funny enough. And that's something that physicists actually use to some degree. I guess the concept of like time, but I'm not too well versed in that topic. So there are multiple different types of rigid motions. Yeah, yeah. Um, so I guess now that we have this concept of isometries, I'm just going to go ahead and define a isometry formally. Um, So we've I guess had this concept of like taking the norm of two functions. Um, for those who don't know or don't remember what a norm is, maybe it's been a semester, maybe it's been a while. I don't know if you're in the free what's the linear algebra reading group. Uh, the length between two vectors itself noted as the norm of such values. So norm of values. The text itself does like to simplify things and make it an R2. In R2, it's easy to think of these norms as just the absolute value of such, but I guess it makes it a lot more easier to look at these as actual I guess norm operators because this literally just takes the square root of u1 minus u or minus v1 plus so forth, if we recall from linear algebra. Um, there's no inherent difference. These norm operators will still function regardless of what you do, but going forth, an isometry in Rn is a distance preserving map. map um, f from Rn to itself, such that for all u and v in Rn, the norm of such functions, f of u minus f of v, is equal to the distance between these two functions as well, or the distance between these two maps, or the domain elements. I'm kind of blanking on the terminology. And we call these maps as a figure to a congruent figure, which means it's basically just describing literally what an isometry is or what these rigid motions are. What we mean by congruency is literally the same exact as saying same shape, lengths. This is kind of thick, but I'll stick with it. Lengths and same shape, lengths, and angles. From if you remember back in like high school or middle school, algebra or geometry. So, oh yeah, Lolo, do you have a question?
No, sorry.
Oh, gotcha. Yeah, no worries.
For some reason I can't mute.
Oh,
Yeah, I'll leave this and come back.
yeah. I was taught in physics class that reflections were not considered rigid motions because it inverts the image as a mirror, which can't be decomposed as. Okay. Um, that's really interesting, but well, I think I know the reason why, and which we'll actually get to talk about. I think maybe within the next section or two. But there's these concepts. I think physics looks at more of orientation preserving rigid motions, which is if you've done the reading, kind of like just goes like, oh, it only considers translation and rotational because I think that's more applicable to physics. But yeah, in the world of math, it does consider reflections too. And reflections, anything with reflections is called orientation reversing. So it's not exactly the most handy, but it's good for some parts. So this entire concept of having these, I guess, congruent figures, which we've learned from, like, say, like elementary or like lower education, like K through 12 standards, is that we learn congruent figures as like a geometric term, and it comes back to the idea that algebra really is just a, again, from both the perspective of Artin and myself, it's really just a written geometry. Kind of, I just thought that's really cool, which is, I guess, a headliner for future reading groups. But we could take a look at something that we've talked about in the past as orthogonal linear operators are isometries. So the reason why we do have that orthogonal linear operators or isometries is that similarly, if we take a function from a linear operator or an orthogonal linear operator, let's just label it phi u minus phi of v is equal to phi of u minus v, which kind of has that like homomorphic, uh, I guess, variation. It preserves dot products. And that's exactly what the point of an orthogonal matrix or an orthogonal anything would just result in. It always preserves dot products, and that's the key defining feature of orthogonality. And we also have translations of vectors, which could be an isometry, but they aren't linear operators. So if we had, say, um, so I guess write this as a fact, a translation of a vector is not always linear operators because we don't always have the fact that it's going to be mapping a figure to a congruent figure. So I guess if we take, for example, if we have, say, figure f times 0, this doesn't map it to f. No, it just maps it to 0, which is not the figure itself. So therefore, we don't have a concept of identity at all times, or we don't have a concept of a, like, I guess, an additive identity or the 0 map in these cases. We do have, we kind of force, or we kind of force upon a sort of identity, which is the figure itself in its base form. All right. So we get into our first theorem. I don't know why it's not going down. I don't want to be particularly working at the bottom of my screen all the time, but we'll see. Let phi be a mapping from R to R, or Rn to Rn. Then the following are equivalent. So we have our statement A says that phi is an isometry that fixes the origin. And if that hasn't already started buzzing some sort of like alarm bells in your head about fixing the origin, since we just talked about how the origin doesn't always go back to the identity itself, um, it should help, I guess, give us a bit of a leeway or a bit of like understanding to this next concept of phi preserves dot products. And what does that mean? The combination of these two would immediately imply that phi is a linear operator. And I thought personally this was definitely a bit more easier to see compared to most theorems later on in this text. Because we've just kind of given an example, we laid down a foundation that, oh, a translation isn't always a linear operator because it doesn't move the origin itself. It just because we have a mapping with the origin doesn't actually equate to the origin itself, but there is a form of identity with this. So, in order to prove this theorem, I want to first off introduce a lemma. If the three dot products x times y, x, or x dot y, x dot x, and y dot y are equal, maybe I should have, then x dot y, or x equals y. All right. I feel like this was a pretty seeable proof. Oh yeah. I feel like this was a pretty seeable proof since we have x dot x, or x minus y dotted with x minus y, then x dot that's equal to kind of like what we have with foiling. We have x dot x times we have minus 2 minus minus 2 x dot y plus y dot y equals 0, since these are the same statement. So because this is true, in fact, we have all of these. The only way that this is true to equal 0, we must have x is equal to y, or x minus y is equal to 0, which implies x equals y. Let's go ahead back to the theorem itself. So I'm going to go ahead, prove the direction from B to C. Um, we're going to do this first, and I guess the textbook does this first in order to, I guess, lay down the foundation in order to prove A to B. But it just allows us to be able to, I guess, have some defining variables that we could use later in the future. So let phi be a map as given that preserves the dot product. We want to show phi is a linear operator. So given x in R, n, let w, let our variable w equal u, yeah, u plus v, and phi of w equals phi of u plus phi of v, such that x is equal to phi of w. And similarly, y is equal to phi of u plus u of phi of w, or v. Then, by lemma, um, x is equal to y, which that's what we're given by the statement itself. Um, since phi preserves dot products, then x dot x is equal to w dot w, and x dot y is equal to w dot u plus v, and y dot y is equal to u plus v dotted with u plus v. Hence, phi is orthogonal by our lemma. CV. So now our next step is that we want to show that phi of u is equal to phi, or c phi of v, which again comes back down to what we want to show with linear operators, that there's some sort of, I guess, semi-homomorphic, uh, I guess, products or values with them. Um, if we let x is equal to 5u, so we're going to redefine x, and y is equal to phi of v, or phi of cv, then x dot x is equal to phi of u times phi of cv, which is the same as saying phi of u times c phi of v, which by dot products, we just take this to the outside and just have c times phi of u times phi of v. Do we have any questions so far? All right. Okay. So now our next statement is going to be proving from A to B. So let phi be an isometry. That fixes the origin. Then phi of u minus phi of v dotted. Yeah, go ahead. Uh-huh. Yes, yes, and that's why we have, like, these homomorphic, like, values to just show that's additive in itself. If we could show that we can in fact take the constant outside, similar to here, and we could also have this, let me go above. We could also have the fact that phi of u plus v is in fact equal to 5, u plus 5 of v, then it shows that it's in fact orthogonal. It's basically establishing we already have an orthogonal, um, product because of the fact that we have these dot products. So sorry, because it preserves these dot products, all we just have to show is that it's a linear operator. So we have, I guess, like, one half of it, we just have to now show that's a linear operator. I guess I could say that this is an orthogonal, linear operator, but it just follows. Yeah, no, I should have said that. Yeah. Yeah, no worries. So, on this next part, all we're just trying to show is that specifically, that we let me double check. Yeah, so since we're fixing with the origin, we're just trying to show that it preserves dot products. And so, I guess taking upon what we did from the lemma previously, we could kind of like pull up the same exact conclusion of just saying if we dot these two products of the same value, phi of u minus phi of v, since we're dealing with the origins themselves, then that's equal to u minus v dotted with u minus v for all u, v in R. Let v be 0, then phi of v is equal to phi of 0, hence it's equal to 0 since we're fixing the origin. Thus, phi of u dotted with phi of u is equal to just u dot u. Similarly, for phi of v. So with this now idea, I guess present, we could just show this by having the statement up above previously dotted with itself equal to phi squared of u. Or I shouldn't say phi squared, that was my bad. Phi of u dotted with phi of u minus 2 phi of u dot phi of v plus phi. I'm gonna drag this to the left a bit. Plus phi of v dotted with phi of v, which implies that I'm just going to label this as, or not, we don't have to label it. Take this underlined portion, and that's exactly the same as saying u dot u plus 2, or not plus, 2 of u minus or u dot v plus v dot v, which implies that we could take out these. Probably should have actually written down this equation. We could take out these, I guess, products here. So I'm going to actually undo that. And we're in fact we're left with negative 2 u dot v is equal to negative 2 phi of u dot phi of v. Hence, it does preserve dot products. All right. So what happens if the origin's not fixed itself? If phi of 0 equals some value a, which is a, I guess, the origin in another function f, or not another function, another figure f. So since f is an isometry, then we know f is just translated. Hence, we denote this movement, this function actually, not movement, as phi is in fact equal to the translation, we're going to denote it t, of negative a with the figure itself, and we're going to note this as the translation. Did I say translated? Oh, my bad. Oh, yes, translated as in like it's literally just been moved. Is does that clear things up?
Sorry, can you repeat what's the what are we doing here?
Okay. So we're basically just defining the function, what like I guess phi itself is actually equivalent to. So we basically just
Mhm.
said previously that we're dealing with phi to be a mapping of R n to Rn. But now we're actually defining that by saying if we have some sort of figure um, A, we're mapping this to a we're defining this function to the figure itself so that we now have an isometry that's in this case phi is just a translation of that isometry.
Okay,
Does
I see.
does yeah, okay. From MM to O then. Okay, so we've dealt with these concepts of orthogonal groups. um, orthogonal groups. Or, not instead of saying orthogonal groups, I think you guys referenced them as orthogonal matrices. Um, and we're gonna reference Mn as the set of all isometries in Rn. Okay. So the map pi, which is from Mn to O of n, is defined by dropping the translations of an isometry. So if we have a function, say, um, f is equal to translation of a phi, then that implies pi of f is just phi. Prop. So we now have a proposition that we're just trying to prove that pi itself is a surjective homomorphism. Surjective homomorphism. Such that its kernel k is just equal to a singular element, the translation of v, which in fact is normal to this set of isometries. So are we just talking about geometric transformations? Yes, literally. So we basically just talked about previously, um, I guess like how algebra itself is a written geometry. And so we're looking at, I guess, examples of this through these concepts of symmetries. So this could be your, if we scroll up above, this could be your, I guess, bilateral, glide as rotational and translational. And we have the concept of like rigid motions, these concepts of isometries, which is basically just taking, say, like, I guess something that you learned in regular like geometry, just taking a figure and being able to rotate it, or taking a block and being able to rotate it any sort of way, and it preserves the same exact properties. So we're now basically just looking at this chapter. We're literally defining these properties of, oh, because they are the exact same figure, because they have the exact same lengths, angles, as well as the form and shape of this figure, it in fact is just a group of these it's a group of these symmetries or these isometries. So now that we have, yeah, no worries. So what we're trying to prove here is that if we take these sets of isometries and we map them over to the orthogonal matrices, we can in fact get a surjective homomorphism. So suppose F and G are isometries such that F is equal to some sort of translation of phi, and G is equal to some sort of translation of psi. Then Fg is equal to T, the translation of A plus B of phi and psi. Therefore, or then phi of f. Oh, I think I made a mistake. Yeah. Then pi of fg is equal to phi and psi, which, funny enough, is it comes out that this is actually just a homomorphism of phi, or pi of f times pi of g. And similarly, if we have h is equal to the translation of x, or translation to x, then pi of h is just equal to phi for all h in Rn. Then pi is surjective. So I think we got to a point in the text where we're kind of like getting into change of bases. And I felt like this is really kind of sticks one to one with how we describe these linear operators and compositions. Um, if need be, I could definitely open up the textbook and we could talk about it, but I felt like this was something that should have been given in previous lectures, and I felt like it was something that's strongly established, like the change of bases back in linear algebra. So if you had, say, a basis of b, which is just equal to 1, then that's isomorphic to b with a basis in, um, say, -1. And these changes of bases should still work regardless of how you do it. This is just, I guess, basic linear algebra that I'm just going to go ahead and skip over instead of having this super elongated. But we should, I guess, talk about these determinants that comes out of these bases. So we recall that a determinant recall that a determinant on an orthogonal operator is plus or minus 1, denoted as orientation preserving, and minus if it's orientation reversing. And this kind of goes back into what I don't know how to say your name, but this kind of goes into example of what whatever, I guess, Anders mentioned before about how in physics there is not a concept. Anders will be fine. Okay, cool. There's not these concepts of, like, say, reflections as rigid motions in physics classes, or did I say reflection or preserving twice? My bad. Um, and that's because we have these concepts of orientation preserving and orientation reversing. And what that basically just means is that we could think of these as preserving. So we'll just take +1. I'm just going to note that as anything that's translated and rotated. And -1 is anything that's reflected. Uh, so if we have this, I guess, say like t, and we have this translation of t, and we also denote rotations as rho of theta, then that's an orientation preserving. But if we have, say, the same exact T of alpha, TA, rho of theta, and let's say we have a reflection, then that's immediately a orientation preserving or orientation reversing. So it's just saying that anything that has some sort of reflection is in fact orientation reversing. So sorry, I didn't see your question before. Does that have something to do with Euler angles? What do you can you explain what you mean by Euler angles?
Euler angles are just essentially a way of like rotating something in a way that like it's like an angle relative to its origin, I guess. Kind of hard to explain on the fly.
It's
Uh,
rotating something such that it's relative to the origin.
Kind of. Think of like I think it's like rotation. Think of like rotation in like computers or like
Oh, like a fixed point.
yeah.
Okay, yeah, no, funny enough, yeah, we will get into that. I don't know they were called Euler angles, but we will get into that. That's something that later on is going to be called the fixed point theorem that we'll definitely do in this lecture. Um, so yes, in some sort of way, but the orientation reversing and preserving part doesn't actually have to do with the fact of these Euler angles. It has to do with more so congruency. So if we recall, congruency is the same exact shape, angles, and form, or say shape, angles, and length. And I previously said, I don't believe you were here earlier, but I previously said is that if we take a shape, say like an L block, and we reflect it so that it becomes this, no matter what rotation or translation that we do on this, say E and R, or E and F, regardless of what rotations or translations that we do on E, we would never get to F with translations and rotations. It's just not possible. And you could definitely do this. I guess it's like a fun exercise voluntarily to put on any sort of block or any sort of object, whether that be a really cool plus sign. Um, well, I guess a plus sign would be bilateral symmetry. So that's gonna be there's a couple of exceptions with these, but um if you look at these like say non bilateral symmetries, then you would have these orientation reversing just not being able to coexist with this congruencies. And the reason why it may work for some, may not work for others. For example, what I mean by plus sign is this, regardless of how you reflect it, it would still be the same shape. Though it looks the exact same, it's important to generalize it because this is kind of like verging into concepts way, way further in math, like graduate level math called like Lie algebra. Because regardless of how, or even just to say a square, regardless of how you may play with the objects, just because it looks the exact same or may have the exact same elements, it's doesn't actually have the same features. And that comes with like say like dihedral groups. I don't know if that was done in introductory to groups, but like dihedral groups or even like um, basic, for example, symmetric groups even they don't have this concept of just because you reverse even though it looks like the same shape, it's actually the exact same. And that comes back down to just concepts in Lie algebra. This is something like kind of like from a graduate level. Maybe Stucky would be able to tell you about that. Making every point. Yeah, yeah, no, literally, it would just be like making every single point a unique letter, or a unique color. I think that's actually one of the. I think that's definitely a better. That's definitely a better way to describe. If you even if you had every single color being different, if you reflect it, they would not be the same, or they will not end up the same. Yeah, that's a right. Um, so coming back to these orientation reversing and orientation preserving, it creates this concept of special orthogonal groups. So we define special orthogonal groups, SON, as all elements, let's just say O in O of n, such that the determinant of O is equal to +1. Because, and this is what we look at specifically in physics. And actually even in chemistry too. Um, so yeah, I'm guessing the molecules aren't the same as the reflection. There is that concept, but at least from my perspective, I seen it applied in chemistry with more so with crystallization. I did a whole semester on, I guess, reading research papers on like crystallization with applicants into the algebras, and that's where I saw personally where this SO or special operator group really matters. Um, but I wouldn't be able to say yes or no specifically about molecules. I just know for just crystallizations. Um, but I would say perhaps that sounds plausible. Yeah, no, um, definitely not me. All right, yeah, and I guess to expand upon that crystallization aspect, if you've taken like say even like linear algebra course, you've probably seen the function of phi of theta, or phi of theta is equal to this matrix cosine of theta, sine negative sine of theta, sine of theta, and cosine of theta. Um, which is literally just which is basically the same exact as saying our rho of theta. It's our reflection, and we're rotating across an angle theta. So if you take this, say this function, it's really just a mapping from some sort of real number to the circle itself, which we denote this as the circle group. And the circle group is in fact congruent to the special operators of n. And that's because if we take any sort of value on the circle, it should be able to, you could translate it, or you can reflect it all you want, but kind of similar to what Kirby said actually. If you take these points on the, say, origin, I'm going to note them as blue and red, then if you reflect it, oh, where's my blue? Oh, if you reflect it, it does happen to be orientation preserving actually in this case. So that's a rare example. So that's actually nice to know. Yeah. Um, Another applicants to here is, for example, if you look into again the algebra, you look at the operations, you look at, I guess, functions with the special orthogonal groups. Um, mapping to higher dimension objects in 3, 4, 5, or 248 dim 248 dim polytopes. And I just thought that was really cool, and especially when because it's like 248, or I think even like 127 maybe. Um, these are specifically dealing with these concepts in crystallography. Crystal. Yeah. So I thought that was a little bit of a fun fact. So coming back, I guess, into this algebra, since we kind of went on to a little bit of a tangent. Um, let's denote translations by vector A such that if we have a fixed vector, say x plus A, and we could also denote rotations as theta, or I guess we should say rho theta, which is equal to this matrix. And then we could also do reflections denoted by R, and we only have one element in this rotation, or this reflection, which is just 1, 0, 0, -1, which is kind of similar to the identity map, except for just reversing the last segment. And that's your 3 different types of rigid motions that we're specifically looking at. All right. All right. Okay, I think this is like the final stretch. I could definitely do this. This is like the most I've sat down if I'm like I don't understand how professors did it during COVID, especially like during grad classes if they have like 2 or 3 hour long classes. Can never. All right, cool. Okay, yeah. All right, so we're starting a new section in the text. Um, am I even one to one with the text? I have zero clue. Yeah, I'm pretty sure I ended off on 5.4. For some reason, yeah, okay, I'll take it. Interesting. I don't know why. I just only have like 3 sections really labeled. Must have missed a section here and there. So, oh, 5.3. Okay, interesting. I basically modeled it after the second edition, which is what I have. But like I still like I guess Fo sent a Fieldsmo sent a download for the old text. And I was like, okay, like this looks fine. It's just it's very clunky. It's a lot of I guess unneeded exposition for not a lot of context. So we're going to start defining these terms that I used a bit earlier with I guess dihedral groups, but also something called a cyclic group. There exists an integer n such that g is one of the following. So a cyclic group we're going to denote as Cn, and notice that we're specifically working with two-dimensional orthogonal groups. So Cn is a cyclic group. I guess kind of similar to how we defined cyclic groups before, of order n is generated by rho of theta such that theta is equal to 2 pi over n. And similarly, we have dihedral groups. Two n generated by rho of theta, which is our rotation, reflections, just rotations and reflections through origin. This is one of the cases where I felt like the text was really overly, I guess, descriptive. Because take a look at this proposition. So the dihedral group dn is generated by two elements, x, y, such that x to the n is equal to 1, and y squared is equal to 1. And x times y, or yx, is equal to x inverse y. Then dn is established as the elements from 1 x squared to x to n minus 1, y, x, y, x, n minus 1, y. Can I scroll up for a moment? Yeah, sure. Here you go. If x to the n is equal to n equals 0, okay. Yeah, no, we could definitely go over that. Cool. So how can I explain this? Okay. Okay, so let's just say that we're dealing with let's say we're dealing with the additive group of z 7z. And that's denoted by the elements of 0, 1, all the way to 6, right? So we're established here. All we're doing is adding 1 plus 1 plus 1 and so forth, plus 1, right? So when we have group operations of, say, xn, that's actually a really fun type of group operations. It's known as a cyclic group. So that means x times x times x times x would eventually go back to equaling 1 in itself. So if you take, say, um, yeah, kind of like modular arithmetic for sure, but instead you're now dealing with a cyclic group of using multiplication. And in fact, this cyclic group itself, if this cyclic group was part of a bigger group, say like for example, we could take Z4, I think. Yeah, Z4, right? Yeah, Z4. We have the elements of 0, 1, 2, 3. In fact, 2 times 2 is equal to 0, which is the identity. The same idea over here, except we're now dealing with just any element x, which is just a uh, figure that's either being rotated or translated again and again is in fact just equals to 1. And if it hasn't also been a bit more clear, x itself is going to be our rotations. I don't know why it's so thick. X is going to be our rotations, and y is going to be our reflections. And as a corollary of this, um, D2 is isomorphic to S2, the symmetric group, or S3 actually. Because notice that S3 has 6 elements, and D2 has 2. Did I do this right? Oh, it said D2. Whoops. 3 factorial elements, and this one has 2 times 3 elements. Um, and in fact, there's no further isomorphisms for anything greater than 3. All right. And I guess like another, key piece of information is that D1 is generally denoted as kind of like a teardrop. Let me draw that better. D2 is noted kind of like an eye, like a football. D3 is denoted as a triangle. D4 is denoted as a square, and so forth. And so forth. And we kind of call these, instead of saying like they're their official terms, we kind of denote these as, say, fivegons, because they don't have to be specifically pentagons, um, triangles, and squares. So if like an algebraist ever comes up to you and goes like, "Oh, look at that 3-gon," or "Look at that 1-gon," think of these as just dihedral groups. Why wouldn't D1 be a circle? D1 wouldn't be a circle because it has no edges. So these dihedral groups are specifically counting the amount of edges each of these has. So a circle, in fact, would be, I guess, similar to D0 because it has no edges. Some people do actually note this. Yeah. Anders is actually right. Some people do note this as D infinity. I feel like it'll be a circle with the dots. Yeah. So last but not least, let's gamma be a discrete subgroup of Rn. Then either gamma is trivial actually, or gamma is equal to z and z. The proof of that. Yeah.
Subgroup that's discrete.
Wait, what? What's a discrete subgroup? Discrete literally just means finitely elemented. So finite. You don't think so? Oh, you're right. You are right. My bad. Or separated. I think the textbook actually mentioned that. I just forgot it. Um, yeah, yeah. My bad. If A and B are distinct elements of gamma, A not equal to B, and since gamma is a group, A minus B is in gamma, and A minus B
Seriously, not.
is greater than epsilon for some epsilon greater than 0. So we take this epsilon as a distance metric, kind of, as a minimum distance between elements. And yeah, this kind of does actually explain what discrete is. Kind of like just saying that they're all sort of separated, kind of like what Stuckey said. So since only finitely many elements separated by epsilon can fit into a bounded interval, then a bounded interval is finite in gamma. Suppose gamma is not trivial. Then gamma includes b that's not equal to 0. Thus, negative b is also included into gamma because it's a group. Say a prime is a positive element. Then we choose the smallest positive element a in gamma such that we now have a bound. We have a bound from 0 to x, 0, or x is between 0 to a prime, such that a is the smallest element. We want to show that gamma is equal to z a z. So is a prime being positive elements means that all of its coordinates are positive? So we're specifically dealing with integers themselves, so that would not be the case. God, you're right. And we're just trying to prove, yeah, no, yes, yes. So we're yes, we are dealing with specifically the real numbers. Okay, yeah, you're right. So yes, so we are dealing with the fact that where is it? A prime is a positive element. This could be any sort of positive element. We're gonna rewrite this as an A prime. R n. Yeah. Okay. And so therefore A is also in Rn. Yep. Does A being in positive elements mean that all of its coordinates are positive? So coming back to that question, yes, yes, it does. So we're dealing with specifically, I guess, like the first, could say quadrant, but we more so should specifically say like, I forgot the terminology for a multi-dimensional or an n-dimensional on octant, yeah. We're dealing with specifically the first octant. All right. So since we've established that A is within gamma, and gamma itself is also a group, and ZAZ is a subgroup of gamma, what we're trying to show is that gamma is also the subgroup of ZAZ. So let B be an element of gamma. Then B is equal to RA. Such, yeah, go ahead. Okay, yeah, because of the fact that gamma itself is actually a group, then we have all multiples of the element itself. And this is only dealing with the number. This is only dealing with the integers, but we also have like high A, EA, and so forth. We're kind of, yeah, yeah, no, yeah, yeah, yeah. All multiples of A. Yeah. But we know at the minimum that AZ itself is going to be a subgroup of gamma. Yeah, yeah. Have I been? Yeah, I think this is, yeah. Okay. Yeah, yes, we are. Yeah. So, hold on. Sorry, I'm just rewriting all of this really quick. Okay, cool. Um, okay. For some number R in it, for some real number R. Um, take the integer number, your number of R, such that R is equal to M plus R0. M is in Z. And R, since R is a real number, we have uh, R0, R naught is between these values. Since gamma is a group, then B prime is equal to B minus MA. If we recall earlier, we have MA being the smallest number of within this boundary, or the smallest element within this boundary. and we're just taking the number partition of we're just taking the integer partition of A such that we're now just left with B prime at the end. And we know this element to also exist in gamma. And B prime is also in gamma. Oh, so I should clarify these a little bit more. So we know MA is in gamma, and B prime is also in gamma because of the fact that we're just now dealing with I guess since we're dealing with over Rn, kind of like a vector space. So then we have the statement that B prime is between these two bounds. Since A is the smallest positive element in gamma, B prime must be 0. Does anyone want to question why? I guess since we had like a little bit of a kerfuffle, we could definitely, I guess, like sit back and just make sure that we're all on the same page. We good? Okay. I guess moving forward. Thus, B is equal to MA, which is in AZ. Thus, gamma is in fact a subgroup of AZ. I think I messed up earlier as well. Therefore, gamma is equal to AZ. In case I do share these notes, let me go ahead and make this correction early on. Yeah, I did make this mistake. Okay, I see. There. Cool. Get rid of that N. Yes. Since we're now just dealing with, yeah, cool. Thank you. Yeah. Bet. Okay, everything looks clear. Julios. So now that we prove the lemma, let's prove the theorem itself. And this one should be a lot more simpler since we're splitting up into two different cases. If we recall, I'm just going to go ahead and bring back what we had above down here. Oh, I don't know why it's doing that. In either regard, what we're dealing with is specifically, we're trying to prove the theorem back up here that says that if G is a finite subgroup of the orthogonal matrix group O2, so we're working in two-dimensional, then there exists an integer n such that G is one of the following, and n is specifically to denote the order of these groups. So there's a cyclic group of order n, which is all the rotations generated by theta equaling 2 pi over n, and we're dealing with all the dihedral groups of order 2n, such that we're dealing with both the rotations as well as the reflections through the origins. So with that now in mind, I don't know why I couldn't copy and paste it, but with that now in mind, let's prove this theorem. So let's go ahead, state our assumption. Let G be a finite subgroup of O2. And then we're dealing with case. So case one, suppose all elements of G is a rotation. So if that's the case, what this is trying to prove is that, oh, we're showing that it has to be a cyclic group, right? And that's basically what the definition of cyclic groups. So we want let gamma be the set of real numbers a and theta in R such that, or a and such that rho of theta is in G. Then I should clarify this. R such that rho of theta is in G. Then gamma is a subgroup of the additive group R plus and contains 2 pi. Since G is finite, then gamma is discrete. If we recall earlier, these are separated values or distinct values in a group. Discrete subgroups, so we're dealing with specifically separated by theta. Or separated by epsilon. So gamma has the form. Yeah, I corrected myself here from now on. There we go. So thus gamma has the form AZ, as we've shown it from the lemma. Since 2 pi is in gamma, then recall since gamma is finite, or since G is finite, then we have, in fact, A is equal to 2 pi over n, which is the order of, where n is the order, sum n. N is the order of the group itself. Hence, G is equal to Cn. So then our case 2. So what if it has both rotations and reflections? So at minimum, let's just say G contains a reflection. Let H be a subgroup of rotations in G, and we've shown H is in fact some sort of cyclic group generated by a rho of theta, is a cyclic group generated by rho of theta. Then 2 pi, or 2 n products, um, rho of theta to the k times r, or rho theta to the k, and rho of theta to the k times r are in G. So G contains the group Dn. Take G in G, then it is either a rotation or a reflection. If it is a rotation, then G is an H, and we've shown that's cyclic. So therefore, or then H is also a subgroup of Dn. So G is in Dn. If it is a reflection, then in G equal such that G is equal to rho of theta to the k times r for some um, rho of theta to the k. Hence, G is in the dihedral group again. All right. So, Stucky, have you been here for all the lectures so far? Okay, gotcha. Yeah, yeah, yeah. Have they gone over orbits? Okay, because I was really curious because for some reason the fixed point theorem does build itself upon orbits, but like orbits I haven't seen are introduced until chapter 6. So we could definitely, I guess, give like a little bit of a preliminary approach of what an orbit is, like kind of like surface level, but I wouldn't want to go too far in depth because it requires these concepts called acts, which is nice, which we're gonna put it in a nice form for now, but it's gonna be a lot more different in the future because Act 1 orbit. Yeah. The concept of having something that acts upon a element in a different set, it looks nice in this regard, or at least I'm gonna frame it really nice. But when we get to, I guess, further group actions, I think that's literally what the chapter name is called. Um, there's a lot more, I guess, useful properties that comes out of this, that rises out of this. The action is so we're just going to define the orbit such that g times a, or all g times a, such that g is in g. And I'm going to note this as O of a. Oh, the orbit of a. All right. Yeah. Okay, cool, cool. So the fixed point theorem states is let G be a finitely or finite group. Oh, that's weird. A finite group of isometries of the plane. Then there is a point in the plane that is fixed by every element in G. It kind of gives another definition of an orbit, P, such that G of P is equal to P for all G in G. Let me go ahead. Let me go ahead, pull up the textbook really quick because I think I got this segment wrong. That doesn't sound right. Do we know what theorem is the fixed point theorem? Top of section 4? Okay. Gotcha. Okay, cool. Okay, I see. Okay. Julio's. Okay, so O of P is equal to P for all G and G. Okay, so let S be any point in the plane and capital S be the set of points that are images of S under various isometries. And what we mean by images is that we denote these images as translations, reflections, and rotations. In G. So each element S prime in S has the form O of G in S of S is equal to S prime for some G in S in G. This set is just kind of called the orbit of, is called the orbit of S under action of G. The element S is in the orbit since the identity I'm going to denote as 1 is in G, and S equals 1 times S. So therefore, we could also think of this orbit as G is the group of symmetries of a regular group of regular pentagon is depicted below with the fixed point P. So we could think of these pentagons as, I guess, being able to move each of these points to another value. So let's call this identity S right here. I'm gonna label that red. And then we have a fixed points P, which is going to be our origin at the center. And we have different symmetries according to whatever case that we look at. So we have a reflection across the origin, which is going to be through S. We also have rotation at all these points. Which creates different pentagons, if I actually do this correct. There you go. All right. So okay. So we have these groups of a pentagon, or we have like the rigid motions of a pentagon using this group of symmetries, and we're going to denote all these elements to be points in G in itself, or we can denote all these, I guess, variations of the pentagon to be a element of G. So this pentagon with its points is going to be fixed around some point P, which is kind of like we could think of it as some sort of orbit around P. So sorry about that. I got a little bit distracted. Um, Kirby, do you have a question? So is it kind of like E of theta, but around? Oh, is it kind of like okay, E of theta, but around any point? We are going to establish it around. We're doing rotational symmetries to begin with, but when we get to dihedral groups, we could really just think of it kind of like we could include it as rotations and reflections. But with this fixed point theorem, we're not only just doing that, but we're also thinking of it, thinking of it as in a kind of like a grid, kind of like a lattice structure, as what Stuckey said, which we'll probably talk about in the next section, which would honestly probably pushed back to another lecture. But we could think of these as infinitely many points that create a or we think this as infinitely many points that create a pentagon around this point P. And what we're just choosing is that we're choosing a specific we're choosing a specific P to focus our center on, when even though we could choose, like, say, for example, let's say we're sticking out here, and I'm going to call this, we could choose the center right here, and we call this P prime, and we could also have different values of the pentagon up here. We're just looking at specifically like different cases of these orbits around P's at whatever point that you choose in itself. Does that make sense? So I guess like I guess if it makes it a lot more easier to understand, is that if you have, say, a lattice, which we've established previously as being a part of AZ, or our gamma being part of AZ, we are specifically choosing, say, a point P here, even though it could be any point, and constructing a pentagon from those values around that point, and just having an orbit there. So we're kind of like, I guess, a little bit like kind of like bounding this this area. So any element of G will permute the object, or not the object, the orbit S. Yep. Orbit S. In other words, if S prime is in S and H is in G, then H S prime is also in S if S prime is equal to GS, then since G is a group, then HGS is also in S. And that's just because we're taking the multiples of H and G, or the product of H and G from our G values. And that's basically what we're doing here. So given that H and G can be either a translation, a rotation, or a reflection, we're computing all these values of theta of around this orbit with specifically all the values of G in this rotation or in this area itself. And in fact, HGS is just equal to HS prime. Then we list these elements arbitrarily as S is equal to S1 all the way to Sn, and this center point P, or the centroid, or the center of gravity of the orbit, is defined as the averages of all these points. Computed by vector addition. If G's and G permutes the orbit of S, then it sends S to S, therefore P to P, which just means regardless of how we permute this order of S, we will always have these fixed points P being constant. It has been 2 hours, so I think I might have to put this off to another time. I did really want to talk about these different types of discrete groups of isometries, but I feel like it might run a bit over time.